Hi, my name is Encinas Acosta, and I'll be talking about the design of the TPX luminometer for the CMS experiment at the High-Luminosity LHC. This is a work done in collaboration with Dr. Jose Feliciano Benitez Rubio, and in this work, I'll be presenting the design and the expected statistical performance of the Tracker Endcap Pixel detector as a luminometer for the CMS experiment. Uh, Luminosity measurements rely heavily on the precise determination of event rates for a given luminometer. So it's really important to maintain low event rate uncertainties during the calibration of the luminometer and during physics runs, since this is not the only source of uncertainty for luminosity measurements. The CMS detector will receive several upgrades during the high luminosity phase of the LHC, one of which will be geared towards the tracker portion of it, specifically the TEPX detector, from which this 4-in-1 will be designated for luminosity measurements only, and it will utilize the pixel cluster counting method as the main source of luminosity measurements, where the PCC method takes advantage of the high number of pixel clusters. Takes advantage of the high number of pixels and the relative low occupancy of the TPX detector to provide precise luminosity measurements. Luminosity can be thought of as the ability of a particle collider to produce meaningful interactions between colliding bunches of particles, and these interactions are called events, and the rate of these events is directly proportional to the cross section, which is the likelihood of that event taking place, with the proportionality constant being the luminosity. And this can be shown on equation number 1. The detector design. The TPX detector is located at each extremity of the tracker portion of the CMS detector, and it has a range of 175 centimeters to 265 centimeters on the Z direction, and has a radius between 64 millimeters and 255 millimeters. The detector is composed of 4 double-sided discs, each one made of 5 concentric rings of pixel modules, and to guarantee hermetic coverage, each ring has a different number of pixel modules to compensate for the layout and the gaps left by the square modules. TPX is composed of 800 million pixels distributed across an area of 2 square meters, and it will operate at a trigger frequency of 75 kilohertz during physics runs. As mentioned before, this 4-in-1 will be designated for luminosity measurements only. This is because it lies at a zero rapidity of +4, and since there's a really low number of tracking points in this area, this region, this 4-in-1 wouldn't be suited for tracking purposes. In this picture right here, we have the layout of this 4, in which this 4-in-1 is highlighted on black right here. The ring consists of 20 modules, and it has an inner radius of 62.9 millimeters and an outer radius of 107.69 millimeters. And finally, it is expected to run on a trigger frequency of 825 kilohertz to several megahertz. But before any luminometer can be used during physics runs, it needs to be calibrated, and this is done using a Van der Meer scan. The goal of the Van der Meer scan is to calculate calibration constant called the visible sigma, and this is done parting from the fact that the instantaneous luminosity, let's say for a bunch crossing, can be calculated from beam parameters as shown in equation number 2, where N1 and N2 are the number of protons in each bunch. F is the trigger frequency. For the LHC, this will be 11,246 Hertz, and sigma x and sigma y is the overlap width and the x and y direction, assuming the proton densities are factorizable. To determine sigma x and sigma y, a Van der Meer scan is performed, which consists of measuring the rate recorded by the detector as a function of the beam separation, and this is done in the x and y direction separately. Once this is done, Gaussian function it's fitted to the data, and the width of that Gaussian function will correspond to the sigma x and sigma y respectively. This is all done at a low pileup, which means that we have a low interaction rate per bunch. So using equation 1 and equation 2, we can solve for sigma visible for sigma. In this case, it will be sigma visible, and we will have the expression to calculate sigma visible. It's important to mention that sigma visible and the cross section are not the same quantity. The cross section is related to the physics of the event and is the likelihood of that event taking place, while sigma visible is a calibration constant that corresponds to the luminometer and it's specific to that luminometer. And finally, we have the statistical performance for PCC and the linearity performance of the TPX luminometers. First, we have the statistical performance for physics ones, which is done a pile of 200. And in this table, we have the statistical performance for one bunch during 1 second iteration period and 2,748 bunches for 1 second iteration period, which it has statistical precision well below the 0.2%, which is really good. For Van der Meer conditions, these are done a pile about 0.5, and we have the statistical precision for one bunch and 1 second iteration period, and one bunch and 30-second iteration period. Using the one bunch and 30-second iteration period, we can calculate the statistical precision for sigma visible, which is presented right here, which we have for one bunch and 150 bunch, and we can see that even for one bunch we have statistical performance well below the 0.5%, which is really good. And the graphs on the left show the linearity of the PCC method, and this was done using simulations, and the graphs show the mean number of clusters per bunch versus the pileup. The first graph shows this for TPX, where each line corresponds to a different disk, and the second graph shows this for this forming one, and it is found that the deviation from the straight line is less than 1%, which goes to show that the statistical performance of TPX is really good. Finally, in conclusion, the statistical performance for pixel clusters counting for TPX and TEPXD4R1 is well below the 0.1% per bunch per second for online luminosity measurements. This is for physics ones. And for BDM, for the BDM scan, we have a precision well below the 0.4% per bunch per 30-second iteration period, which translates to precision under 0.1% per bunch for the calibration constant sigma visible. Also, both luminometers achieve a linearity deviation well below the 1%, up to a pile of 200. These results show an excellent expected performance for these luminometers for the high-luminosity LHC phase. Well, this is everything. Thanks for your attention. Bye.